Now we'll move to Russia for the final talk for the workshop, and we are back to dynamical maps again, and we have Professor Sergey Filippov from Moscow, who will talk to us about trace decreasing dynamical maps. Professor Sergey?
Can you hear me well?
Yes, yes.
Good, great. First of all, I would like to thank organizers. It seems to be easy to organize an online event, but it's not that easy in practice, as we all know. So first of all, thanks to organizers, and special thanks for honored guests session that was yesterday. And I really enjoyed all the talks yesterday and today. And so I'm very honored to present a talk here at that nice conference too. So previously, in all the talks that we heard previously, we talked about completely positive trace preserving maps. And we discussed Markovianity properties and non-Markovianity properties of them, and some relations with rates, positive, negative, and so on. So today I would like to talk about trace decreasing dynamical maps. So they are much less studied in the literature, but they often happen in laboratory. And my motivation is to consider trace preserving maps, trace decreasing maps, and to show some peculiarities of them. So we celebrate the paper by Sudarshan, Matthews, and Rao. And in that paper, they introduced dynamical matrix that has many interesting properties. And here is a list of them. And if we look at the equation 17, then we see that it is a trace preservation condition. And the authors write that it is still complicated. But we know now that in modern notation, if we use a dual map, then in terms of that dual map, that trace preservation condition can be written as a condition of unitality. So that is for trace preserving map lambda, the condition. So the subject of my today's talk is a trace decreasing map. So lambda is still completely positive, but now we have a relation that the action of the dual map on the identity operator is less or equal than the identity operator. And let us consider a particular experiment where this situation happens. There are lots of such experiments, but one particular form is presented in experimental work by Paolo Mataloni's group from Rome. So they consider all optical implementation of collision-based evolutions of open quantum systems. And surprisingly enough, collision model was established by one of the co-authors of the celebrated paper, namely by Professor Rao. And that paper is actually this paper, Relaxation Phenomena in Spin and Harmonic Oscillator Systems, that was published in 1963. So in 2 years, we can celebrate 60 years of this paper that attracts much attention nowadays, because many people are now developing collision models. And there are actually some reviews on that subject that appeared this year. For example, a review by Italian authors, Quantum Collision Models, Open System Dynamics from Repeated Interactions. This is a review paper. And another review paper by Campbell and Vacchini, so collision models in open quantum systems, a versatile tool for deeper insights. It's also a review paper published this year. But actually many authors worked on this subject, starting from Scarani, Buzek, Zeman, and many others. So this is actually quite a hot topic, and I would like to thank Professor Rao for developing this subject that is, in fact, closely related to modern experiments. So let's come back to the experiment performed in 2018 and reported in 2019 in this journal Scientific Reports. So here we have a collision model where a system which is represented by a single photon, interacts with some sub-environment. And this sub-environment is actually a vacuum mode. And if we didn't have those mirrors here, the dynamics would be perfectly Markovian. But since we have those mirrors, system, our photon in interest, interacts sequentially with that auxiliary mode, and that results in non-Markovian effects. That green box is represented here as a beam splitter, quarter wave plate, half wave plate, and some other experimental devices. But the most important for us is that filter that is used here, FK. So F stands for filter, and that filter is actually a trace decreasing operation. So this filter absorbs photons of some polarization with a finite probability. So experimentally, those filters are given by such plates. So these are actually devices that absorb photons. So absorption of a photon leads to a loss of information carrier. And therefore, we can describe our system by the subnormalized density operator. And this is a description for that. So in fact, when we perform measurements here, we post-select those events that results in the photon detection. So it means that we have a trace decreasing map lambda that acts on our original density operator. And then we should normalize the outcome. So we get the normalized output state. So the authors of this paper actually considered evolution of post-selected state as if it was given by some dynamical map. So in some sense, they considered an evolution which originates from a linear map lambda, but now is given by some non-linear map phi. So phi is non-linear map. So you can clearly see that because we divide by the probability of detecting a photon. Okay, so here on the right panel, you see that the authors also considered an ancilla, which is originally entangled with the system of interest. This situation happens in experiment where a single photon is split into two photons that are entangled with the use of birefringent crystals. So such states are routinely now created in laboratory. So the authors considered the evolution of the system and ancilla, or ancilla and environmental mode. So they used detectors. So again, post-selection was involved in experiment. So post-selected state for that two-mode scenario is given by the formula on the right. So you see that the map is again non-linear. And now the authors study non-Markovianity. So they consider system-ancilla entanglement dynamics. But of course, this dynamics is analyzed for normalized states. Okay. So and let us pay attention to a blue curve here, which is an experimental curve for some transmission coefficient of the filter we have discussed. So you see that the original system entanglement is close to 1 originally, and then it decays, and then it increases. And that increase in the entanglement is treated by the authors of the paper as an indication of non-Markovianity. And they cite two papers, 14 and 36, and these papers are perfectly all right. These papers deal with trace preserving maps. So the results that increase in the entanglement measure concurrence here, they are valid only for trace preserving maps. but we, in our case, deal with trace decreasing maps. So my claim is that this approach is wrong, and it cannot be actually used to justify the data presented in the paper. So let me illustrate this by the following example. Let us consider one qubit evolution where rho is the density operator of a qubit, and we have two states, H and V, with horizontal and vertical polarization for a single photon. Here I have anti-commutator. So that equation describes completely positive and trace decreasing dynamics, and that dynamics is divisible. So lambda t is a divisible map. So particular form of lambda t is given by this equation, and you see that here appear some rates similar to those that were discussed by Darush and Yurki and Genkimura. So these rates are expressed through small gammas via these relations, and we choose particular form of small gammas such that they are always non-negative. So we artificially construct such a model to illustrate a counterexample for the previous paper. So if we look at the exact form for probabilities to detect a photon after the action of the trace decreasing map, these probabilities will monotonically decrease. So they are described by the two curves here. You see the dashed line, black one, and the dotted line here are exactly the probabilities to detect the photon, and they monotonically decrease. However, if we consider normalized state, so the state the authors used in the paper, so you see that it will be a pure state in such a simple case. And that pure state is given by normalization condition here at the bottom. And you see that we can easily calculate concurrence for such a state by usual formulas for two qubit states. So if we calculate concurrence and plot it, we see that it is non-monotonic. So we see that the entanglement monotonic. We see that entanglement dynamics is non-monotonic, although the dynamics is divisible. So it is completely positive trace decreasing, and it is CP divisible dynamics. And the contradiction is easily resolved. Since we have normalization of the state here, then we have some difficulties. So this example shows that observation of the increase in entropy of system and ancilla is not a proper indicator of non-Markovianity if the dynamics is trace decreasing and we actually resort to post-selection. So this is the first observation that is often somehow overlooked in experimental papers. So I would like to focus attention of people who are experimentalists to pay more attention if post-selection is involved in the data analysis. Okay, you may think that this example was too trivial because the operation that we considered was of rank 1. So here I can see the more complicated generator, which includes dephasing part. And this case corresponds to the blue curve here. So it shows that still entanglement dynamics can be non-monotonic, although we have a completely positive divisible dynamics, but this dynamics is for trace decreasing maps. All right, so how can we propose something positive? I mean, how can we generalized non-Markovianity criterion in this case. So, and there is one proposition. So it is motivated by the figure we just observed. You see that when entanglement vanishes completely, it remains 0, and there are no revivals of entanglement. And it is easy to prove the following result. So let lambda be a trace decreasing completely positive divisible dynamical map, and rho SA is an initial system-ancilla state. So if the post-selected system-ancilla state becomes separable at time moment t star, then all future post-selected states remain separable. So if it happens that we observe some non-zero entanglement here after it was 0, it is an indication of non-Markovianity. And this indicator of non-Markovianity is already applicable to trace decreasing maps. So this is a corollary. So suppose the system experiences a trace decreasing dynamics. If the entanglement death is followed by entanglement revival, then it is an indication of CP indivisibility. And clearly this result can be generalized to the case of the Schmidt rank. So increase in the Schmidt rank of the output is an indicator of non-Markovianity. All right, so these results are presented in archive paper of this year. Okay, so there is another important quantifier of non-Markovianity, which is based on backflow of information. A great paper by Breuer, Line, and Piela discusses the quantity, which is a distinguishability of two states, and this distinguishability, if it behaves non-monotonically in time, so there is some increase, it is an indication of some non-Markovianity. And this result is valid again for trace preserving maps. So if we try to generalize this result to trace decreasing maps, then we have several options. So one option is to consider those non-linear maps and consider the outputs of those non-linear maps. So just to take something that is similar to distinguishability. And this quantifier can increase under trace decreasing CP divisible maps, as I illustrate in the paper. So this is not a proper indicator. So another example can be to take probabilities of photon detections. So to consider PIT as a trace of lambda IT acting on rho 0. So this is a probability of photon detection. So photon detection probability. And if we weight our states with probabilities of this form, then we can hope that we get a proper indicator of non-Markovianity, but this is also not true. So this is not a valid indicator either. So what we should do, we should consider the original problem of states distinguishability and calculate the successful distinguishability, probability of successful distinguishability. And if we calculate it, then we get the quantity that is written below. And this is a proper indicator of non-Markovianity in case of trace decreasing maps. All right, after these comments about experimental works, I would switch to some other problems. And another problem is entanglement distribution through noisy channels. So one of the channels is phi1, the other is phi2, and if they are trace preserving, then the solution in case of qubits has been obtained in this paper. So this paper deals with the search of such an entangled state, rho 1, 2, initial state, that stays entangled the longest time. So if we introduced disentanglement time tau, then the problem is to find the state rho 1, 2 optimal, which corresponds to the maximum entanglement lifetime. And the state, so if this state rho optimal becomes separable, then all other states become separable. And separability of the state is given by this equation. So this is a solved problem. But the unknown part was how to generalize it to trace decreasing maps. So if we perform some experiments with post-selection, then we actually deal with trace decreasing maps. And the question is when this density operator becomes separable. And the key tool to solve this problem is to use quantum synchron theorem. So quantum synchron theorem says that a map which is strictly positive can be transformed into a unital map. So unital map preserves the identity operator. And this quantum synchron theorem was derived in 2004 in the paper by Gurwitz, and then rediscovered for completely positive maps in 2015. But the simplest explanation is presented in the paper by Obrun and Sharrock, who also wrote a very nice book, which is entitled Alice and Bob Meet Banach. So I highly recommend this book. So when we apply this quantum synchron theorem, we can transfer the problem to the case of unital maps. And the case of unital maps was already considered in the literature. So we know how the optimal state looks like. So we can use that result to find the optimal state in the case of trace decreasing maps. So these results are presented in this paper published this year. Okay, this is another example how trace decreasing maps appear in quantum problems. Okay, and the title of my talk, the second part of it, was devoted to quantum communication rate problem. So suppose we have some network of quantum computers. Sabrina talked about quantum computations and so on. And for example, we should merge our resources. For example, a computer in Moscow and the computer in Helsinki, we should merge them into a network. So in this case, we should communicate over some lines. But if we communicate over some lines, we should transfer not classical information, but quantum information. So we want to exchange the psi vectors. And this is a problem of quantum capacity. So here I illustrate a simple example where polarization dependent losses are present in the communication line. So such polarization dependent losses can be described by an operator which has two coefficients. pH is the probability to transmit horizontally polarized photons, and PV is the probability to transmit vertically polarized photons. And here I introduce the concept of the generalized erasure channel. It is induced by the trace decreasing map, lambda. And to make the map trace preserving, we should add some auxiliary transformation. And that auxiliary transformation actually shows us the erasure probability, and it has an erasure flag. An erasure flag in practice is simply the vacuum. So the vacuum contribution, for example, in this picture, is the flag of erasure. And I call this transformation a generalized erasure transformation because the probability to lose an information carrier depends on rho in general. So if that probability depends on rho, then we have losses that depend on the system state. Okay, here at this slide, I discuss previously known results for the case of conventional erasure channel when lambda is a damping, and some other results, new one, for diffrasure channels introduced by Leditsky, Lunken, Smith, and some other channels, combination of amplitude damping channel and conventional erasure channel by Sidhu, Griffiths, and others. So in contrast, the case that we considered, it corresponds to the case when the losses are state dependent. And this example is reviewed in the paper in Journal of Physics A, published this year. Okay, I don't know how much time I have to discuss quantum capacity. Could you please tell me? Because I don't know when exactly I started to talk.
Yeah, it's okay. Like, you can continue.
Okay, okay. So as I mentioned, so we want to communicate between quantum computers. So we want to exchange quantum states. And it is actually possible even if noise is present in the communication line. So, and the general theory of information transmission says us that the rate with which we can transfer quantum information with superposition principle and entanglement and that all through the line is given by the quantum capacity. And the quantum capacity itself is that quantity that depends on the channel and is given as the limit of regularized single letter capacity. And single letter capacity is given by the coherent information, which is the entropy of the output of the channel minus the entropy of the output of complementary channel. And complementary channel is given by the Stein-Spring dilation, where we take trace not over the environment, but over the system. So this is actually a quantifier that shows the information that is actually transferred minus the information that is dissolved in the environment. So this is a mathematical theory that is well developed in its final form by Devitak. And there are some particular cases when for example, it is known for channels such that some auxiliary channel and direct channel, and in the case of antidegradable channels. In the case of antidegradable channels, quantum capacity equals 0, possible to clone quantum states. All right, so these were known results, and the open problem in that communication theory is the problem of superadditivity. It may turn out that the use of block codes where multi-letter codes are actually exploited. So many letters are encoded into some entangled states. So when we use that type of coding, we can get a higher communication rates. So here is the definition of superadditivity of coherent information. And it was observed for some channels, for example, for depolarizing channels, for diffraser channels, concatenations of erasure channel and amplitude damping channels, some state-of-the-art channels, and some constructions. And but calculations are always numerical. So here the results are mostly numerical. And here I want to show you some analytical results that are valid for the polarization dependent losses. So if we consider the generalized erasure channel that is induced by trace decreasing at lambda, then it's easy to calculate the complementary channel. And then it's easy to find single letter capacity. And here I plot the diagram for pH and PV, which are parameters specifying the probability of successful detection for horizontal and vertically polarized photons, where I show that additivity condition holds in red region, additivity condition, which is trivial, holds in green region, and there is also superadditivity condition, which says that two-letter coding is better than single-letter coding.
So the use of entangled states helps in transmitting more quantum information. So this is some proposition, but I'm sure that at the end of the conference, all of you are quite tired. So I will simply say what is the main ingredient in the proof. So when we have, for example, optimal codes for single letter scenario, when we consider two-letter scenario, we should take second tensor power of the first state and add some coherences. So here we add coherences, and those coherences help us to transfer more information. Here I give some equations for entropies of the channels. And this result showed that we have superadditivity in the yellow region. Here we have superadditivity. What we don't know, what happens in the white region. And the latest result I want to show you is that superadditivity actually holds in that white region too. So to prove that, consider a subspace spanned by the vector h tensor to the power n-1 tensor v and all its permutations. So it is a subspace of dimension n. And then we consider a well-known W state and modify our construction by adding coherences. So here the term is a manifestation of coherence in that subspace that we selected. And if we now write the channel and consider nth tensor power of this channel, then we encounter binomial coefficients and complex calculations, but we can still pass through that complex calculations because our channel is easily defined, and find the lower bound for increase of the information which can be obtained with the use of entangled states. Of course, it is a lower bound because I cannot perform optimization in arbitrary dimensional Hilbert space, but I can find the lower bound. And you see that there is a binomial distribution here. So the idea is to now consider a limit when n goes to infinity and to replace that binomial distribution by a normal distribution, which has the mean value p and ph and variance, the standard variance. I don't remember exactly how it looks like now, but it is in the paper. The paper is on archive. And this gives us the benefit in asymptotic limit with the use of such states. And we see that the larger the n, so for example, here n equals 3, here n equals 10, and so on. So the larger the n, the greater is the region where we observe superadditivity. And when n goes to infinity, we actually have the whole white region covered by the superadditivity property. So with this, I will conclude that superadditivity phenomenon is interesting, and an example for that interesting behavior is obtained again by the use of trace decreasing maps that induce trace preserving map, which is called generalized erasure channel. All right, I come to conclusions. So my first goal was to focus on trace decreasing quantum operations and show you that they are physical. And I presented you an experiment where they appear. So, and then I just tried to persuade you that experiments that involve post-selection should be revisited, because even if the dynamics is completely positive divisible, some authors overlook this fact and treat the dynamics as if it was linear. So, and this results in incorrect statements.
So then I showed how to merge trace decreasing and trace preserving maps by the concept of generalized erasure channel. And finally, we considered the quantum information transfer through channels induced by trace decreasing maps. And in case of polarization dependent losses, we observed a superadditivity of coherent information that is a strict separation between single letter quantum capacity and n letter quantum capacity. So that's it in my talk. Thank you very much for your attention.
Thank you, Professor Filippov. Very nice talk connecting open systems and quantum information theory. So let me now questions. I see two raised hands. Professor Usha Devi.
Yeah. Very nice. Shall I go ahead?
Yes, yes, yes.
So thanks for a very nice talk. So this, I have one comment that in the paper that you showed about Jayasita Rao's 1962 paper. So that was very interesting. And but what she had done there was a Markovian thing. That is what she did. Relax, refresh, and relax kind of approach. That was Markovian, but you picked from there and you Markovian trace non-preserving kind of maps. But I got reminded of these non-unitary evolutions are any operations generated by a non-Hermitian Hamiltonian. So this kind of things in PT symmetric evolutions, they are also non-trace preserving. In a sense, it is trace deserving. And all that you showed, erasure and in the direct sum form, losses and all that is.
Thank you very much, Usha, for
consider
your
ancilla. Yes.
Yes, yes. So you are absolutely right. This paper dealt with Markovian case.
Yes.
And the Markovian case actually is due to the fact that all the environment ancillas are uncorrelated. And we interact with which of them only once. So what those people in experiment actually did, they interacted with the same ancilla many times. So in this case, it was a collision like that. You see, okay.
Right.
And some people also consider generalizations when a particle collides only once with which sub-environment, but environment itself is correlated. So this is another approach to non-Markovianity. And you're absolutely right. And concerning your second question about trace decreasing maps originating from non-Hermitian Hamiltonians, you're absolutely right. So if I write H as Hermitian part H1, which is Hermitian, plus IH2, where IH2 is also Hermitian, then I can actually consider the unitary evolution, which is induced by that Hamiltonian.
Yeah.
And we will see that it results in the trace decreasing dynamics if H2 satisfies some property. I don't remember exactly. Either it should be positive semi-definite or positive or negative semi-definite. Okay. So
this is, sorry. So I wanted to say in this kind of PT symmetric evolutions, people have noticed some information flow, no backward flow and other things. There is a PRL recently. So I thought it is very interesting to look into that based on your papers.
It is indeed very interesting. Yes.
So that is another, that is in symmetric evolutions. People have seen some additional, that is nice features, which are not seen in general in open system dynamics. So it is this kind of trace non-preserving kind of a dynamics, which gives some other additional features, is what has been being noticed. And even in sensing applications, quantum sensing, and in all those cases, this gives you additional benefit, is being noticed. So I thought of mentioning this.
Yes, you're
Thank you.
absolutely right. PT symmetric systems are now very popular.
Yeah.
Yeah, and I think this is the one, like the one that you
So, but
mentioned.
how do you do it experimentally? Keep on coming there. So you have answered those questions. Thank you.
Yeah, so this 63 papers, like I think nowadays it's known by this Rao refreshment model, if I'm not mistaken, right? Professor
Right.
Filippov?
Yes, I think so. It introduces some fundamental interval here, tau, and yeah. So people who are dealing with collision models nowadays, they know about this paper. They
Yes,
cite
yes.
it.
Yeah, I think recently I've also seen a paper by Mauro Petronzer, like he was also like referring to this. I'll have to dig up again. Yeah, but many thanks to bringing our attention to the 63 paper as well.
So there is a paper by Sudarshan with in
Yeah.
2011 on
Yes, Antonio,
continuous
like
variable systems.
Chimonido and Sudarshan.
Yeah. I think
Yes.
she's also a participant. They also did the same refresh, relax
Exactly.
kind of a thing, but mark.
Yes. I think she was like one of Sudarshan's like last PhD students.
Yeah. Thank you.
So further questions?
I have a question.
Sure.
I don't understand why you find, in some sense, a contradiction when the maps doesn't preserve trace. If you have a map that doesn't preserve trace and you normalize, that's have an experimental meaning. That means that whatever you deduce from that map is given that you are inside the system. Then what you call nonlinear map have a very clear experimental meaning. When you normalize, you are saying, my system doesn't go out, and then you deduce some property. If you take out the normalization, the question is other. You are asking about properties even when the system or part of the system is out. For me, there is not a contradiction. It's like two different experiments. And
Yes,
that is the meaning of Bayes' rule in some sense.
For example, so you see that people say about backflow of information and memory effects, but there are no memory effects in this scenario that I presented, for example. Here there are no memory
But that are two different questions. If you plot the decay, only the decay without normalization, it's an experiment where you don't know if you are in or out. And that is a question. When you normalize, you are imposing that you are inside the system. The system is inside, and that is another question.
I agree with you,
another
but
question, two different questions.
People don't discuss that. And look, that transformation is non-linear. So
yes,
when people write about post-selected experiments, they never mention that they actually consider non-linear maps that they analyze. So they let them then say that they consider non-linear maps for which they observe some behavior. So I still see the problem. But it is more about the terms. And you see, so one more discussion of this plot, for example, you see that the errors increase with the number of steps. Why is it so? Because the probability of detecting those states is getting less and less when we propagate in time. So if the authors include the description of the probability to detect states in the description, then the map would be linear and the discussion would be correct.
Are different experiments. If the map is nonlinear, you are imposing, from an experimental point of view, that it doesn't happen any decay up to that time. That means the normalization. It's like Bayes' rule. You are saying, I am measuring some things, but my system is inside. It didn't decay. If you put out that condition, then the maps will be linear. But for me, are two different experiments. In one, you put a condition. My system is inside, and In that time, I measure some things, and that's give the nonlinear map. If the system, if you take out that condition, it doesn't matter if the system is inside or out, then you have the linear map. There are two different situations. For me, that is the explanation of the difference. But okay, we might discuss later.
Yes, but you're right. I agree with what you say, and yeah, simply interpretation of the results is different. I would like to say that in communication problems, like here in the plot, it is important to distinguish these two scenarios that you have just said, because when we don't know when the signal is going to come, then we cannot actually transfer information. So we should know that the information is within these time beams. So this is what we should know. Otherwise, we can wait for 1 century and get no signal. And some people would say that we still transfer information, which is not correct. So when this information is transferred within time beams, then we should include the loss of particles in the description, irrespectively of our wish, I would say.
Okay, thanks.
Okay, so thank you, Professor Filippov, once again. Thank you for the nice talk.
Thank you for your interest.